Good afternoon, everyone. My name is Jiajie Zhu from Macquarie University in Australia. Today it's my great honor to stand here to present our work, Domain Disentanglement with Interpolative Data Augmentation for Dual-Target Cross-Domain Recommendation. This is a joint work between Macquarie University in Australia, Ant Group in China, and A-Star in Singapore. Now, without further ado, I will introduce our work in the following 6 parts. I will start with the background. As we all know, single-target cross-domain recommendation, termed as single-target CDR, aims to transfer the common user's knowledge. For example, here the common user Alice, transfer Alice's preference from the relatively richer domain to the relatively sparser target domain. However, it has a challenge that it has a limitation that even if for another common user like here, Bob, even if he has reviewed more music than he has reviewed movies, the conventional single-target CDR model cannot transfer Bob's preference from the music domain to the movie domain. To this end, dual-target CDR has been proposed to share common users' preference across domains to improve the recommendation performance on both domains simultaneously. Now let's move on. Data imbalance is an inevitable problem in cross-domain recommendation. So some researchers have already introduced data augmentation techniques, which are commonly used in computer vision field to mitigate the domain imbalance problem between richer domain and sparser domain. However, there are 2 types of methods. The first one is heuristic methods. They mainly emphasize the diversity, usually use some simple rules or a series of algorithms to generate diverse user representations, while they will reduce the relevance between the augmented data and the original data. The second one is model-based methods. They usually focus on the relevance by learning the augmented user representations using some from the original data. So they will keep the relevance, but maybe too conservative and have not enough diversity. So the limitation 1 here is few of these distinct methods can balance the relevance and the diversity of the user item interaction augmentation. What's more, we all know that the data from source domain and target domain comes from different environment, region, or time. So it will lead to different user behaviors, preferences, and item features, and distribution like that. So finding out what to transfer is a key to solving the domain shift. When it comes to what to transfer, it becomes particularly important to reconsider the composition of user preferences. Just taking movie and music domains as examples, there exists domain shared information such as category. For example, people who like watching suspense movies tend to also like listening to suspense music as well, and vice versa. So this kind of information should be decoupled and then transferred to other domains to provide valuable information for cross-domain recommendation. What's more, there also exists domain-specific information. For example, here, the user preference for pictures in a movie, that is the frame in the movie domain. Since it is unique to movie domain, it cannot be transferred to music domain, or it will cause the negative transfer. In addition to these two kind of information, we believe that there should be one more called domain-independent information here. So, for example, here, rhythm in the movie domain means the speed of camera cuts or use of sound effects and the changes in the pace of movie scenes, while the rhythm in music domain means the use of beats and speed of sound and so on. So such domain-independent information should be decoupled, and then they should not be transferred to the other domains, or it will provide useless information or even cause the negative transfer. So the second limitation here is none of these existing methods decouple the domain-independent information. When it comes to the related work, first, the conventional dual-target CDR methods, we can see that they normally have two stages. Firstly, they just mainly focus on to design powerful encoder to get the embedding, and then use a series of transfer layers to get the final embedding. While the disentanglement-based dual-target CDR methods have an extra stage to decouple the domain shared and domain specific user preferences, and only transfer the domain shared information or preferences to the both domains to improve the recommendation performance. However, both of these two types of methods ignore the domain independent information, which is very important and essential in capturing comprehensive user preferences. So what we're trying to do is to try to propose a novel dual-target CDR framework to solve the limitations, and then further decouple the domain shared, domain specific, and domain independent user preferences to capture the comprehensive user preferences. The main challenges are as follows. The first one is how to augment sparse domain and explore potential user preferences, while the second one is how to effectively capture comprehensive user preferences on each domain. To address challenge one, we propose an interpolative data augmentation approach to generating both relevant and diverse augmented user representations. For the second challenge, we propose a disentanglement module to effectively decouple the domain-independent and domain-specific user preferences in addition to the domain-shared ones. So overall, we propose a disentanglement-based framework with interpolative data augmentation for dual-target cross-domain recommendation called data CDR. Here is the overall flowchart of our proposed framework. There are mainly 5 modules. The first one is graph convolution and propagation, and then the first contribution here, the interpolative data augmentation, and then the user preference disentanglement. After that, we can get the disentangled 3 essential components of user preferences, and then we feed them to the information fusion module to capture the comprehensive user preferences, and then feed them into the prediction module, the MLP, to get the final prediction results, and we can finally get the recommendation loss. Specifically for the first challenge, inspired by the mix-up, we just want to generate both the relevant and the diverse augmented user representations. So in order to keep the relevance, we just mainly focus on the common users, and then just linearly interpolate user embeddings generated by GCN in both domains to generating the user representations. While for the diversity, we also introduce the randomness by sampling the mixing coefficient lambda from the beta distribution. I will just conduct some experiments and talk about it later. As for the second challenge, so inspired by VAE and MetaFD mix-up, so we designed this structure to be our user preference disentanglement module. So after that, we can get the domain independent and domain specific user preferences in each domain, and the domain shared information as well. And we also introduce a domain classifier to supervise the disentanglement task. Here, so for domain shared and domain independent user preferences, we try to use them to confuse our domain classifier, while for our domain specific user preferences, we believe that it will be easy to recognize the domain label by only feeding this kind of user preferences into the domain classifier. Formally, just let 1 and 0 denote the category of domain A and B respectively. So given the 3 types of inputs here, so after the disentanglement module, we can get 3 essential components of our user representations. So firstly, we just feed the domain independent and domain shared information into the domain classifier to calculate the KL diverse loss between the prediction and our ground truth 0.5, while we also just feed the domain specific user preferences into the domain classifier as well to calculate the cross entropy loss. And then we will just combine the above 2 classification losses with our recommendation loss mentioned before to form our final loss here. When it comes to our experiments, we just use 2 real-world data sets, Douban and Amazon, and we construct 3 dual-target CDR tasks, and the statistics can be found in this table here. And we also select 9 representative and state-of-the-art baseline models to compare with our proposed data CDR. And the main results can be found in this table. We can see that our data CDR outperforms the best performing state-of-the-art baseline with an average improvement of 8.54% in terms of HR and 11.10% in terms of NDCG in all 3 tasks respectively. And we also conduct a series of ablation study to demonstrate the effectiveness of our each proposed module, like the interpolative data augmentation and user preference disentanglement. And we also check our disentanglement objective, and we find that it could non-desirable disentangled representations. By contrast, we also conduct a series of experiments on the impact of various components of user preferences, which is very important in our work. Domain shared, domain specific, and especially domain independent user preferences. And we especially just try to test whether we should transfer or not the domain independent user preferences to other domain. And the finding is that domain independent information is essential to capture comprehensive user preferences, and it also should not be transferred to other domain. Last but not least, we also conduct the experiments on parameter sensitivity, and the finding we can see that we search in a range of to explore from which distribution we can sample the mixing coefficient, can get the highest quality of our representations. So finally, we just draw a conclusion. Interpolative data augmentation is superior to linear interpolation with fixed mixing coefficient, and it's sampled from uniform distribution yields optimal augmented user representations. And to draw a conclusion, we proposed a data CDR framework, which consists of interpolative data augmentation module to generate both relevant and diverse augmented user representations to augment the sparser domain and explore the potential user preferences, and the user preference disentanglement module to decouple essential components of user preferences to capture comprehensive user preferences. For future work, we plan to extend our module to multi-target CDR, and we can also explore more efficient ways to decouple more accurate and interpretable user preference components. Thank you.
Thank you very much. Thank you, Jace. So questions, please approach the mics. Meanwhile, I will ask a question from that got through the app. And it goes like this. I want to know why to develop dual target CDR methods when we can deploy single target CDR methods twice to perform recommendation in both domains. Thank you.
Oh, yeah. Thank you for the question. We can go back to the slides here. So the question, as I understand, is that why we cannot simply use the single domain, single target cross-domain recommendation models twice to just figure out this problem. I think it's a good question. So actually, the first work of dual target CDR is also from our team. So that means, so they find that even in the sparser domain, there also can be some information like the tags or user profiles or some item features will be relatively richer. But for the conventional single target CDR, it cannot just transfer this kind of information from the sparser domain to the richer domain. So we propose the dual target CDR to try to use the common user as a bridge to do the knowledge transfer. So we can see that as for here. We also have some SDR, that means single domain recommendation baselines. For that experiments, we just conduct the experiments for this domain in distinct domains twice here to show the experiments. But for the single target CDR baselines, we only, because it aims to improve the recommendation performance on the sparser target domain, so we only show the results in the target domain. I hope I have declared this issue clearly. Thank you.
Makes sense. Thank you. Any other question from the audience? So I have one question that's more on the, let's say, level of intuition. No? So you have data sets from two domains.
Yeah.
At least. Okay. And you want to optimize, you had NDCG, I don't remember, some metrics. Okay. Yeah, sure. So why is disentanglement useful in this case? My understanding would be disentanglement makes sense if you want to explain, because you can nicely say, okay, this is domain specific, this is domain independent, and so on. But then you merge all these things again to make the predictions, so you could use another non-disentangled approach.
Yeah, thank you. It's a really good question. So we will come back our related work. So as for the conventional dual target CDR methods, they just fuse all of the user preferences together and just use the transfer layer to get the final embedding. So they just do not distinguish the different components really in the user preferences, just since they have the equally importance. But for the disentanglement-based dual-target CDR models, they make a step to decouple the domain-shared and domain-specific information and to find what we really want to transfer like this. It's a key point here, so it make a step. But for our work, we think there should also be one more like the domain-dependent information. Although we have used the attention mechanism to fuse all of the user preferences together at last, but I think these three kind of information or user preferences are not equally important. We can use the attention mechanism or other information fusion methods to capture the comprehensive user preferences. Thank you.
Okay, so you're saying in a way that too much information is harmful and you want to get rid of the irrelevant stuff.
Okay. We want to make it deeper and deeper to explore the essential components of the user preferences.
Okay, thank you. Any other question from the audience? Okay, then let's have another applause for our speaker. This talk concludes this session, so I invite you to enjoy the coffee break and the posters, and I'll see you back at 4:05 when the next round of sessions begin. Okay, enjoy your coffee.